Dear student, your section 1.1 is evaluating limits graphically and numerically. So today I'm going to discuss the first part, evaluating limits graphically. In this video, I will also explain what we mean by limits. I'm going to use an example from college algebra. Let's say we have a piecewise function. I will let f of x be a piecewise function defined this way. Let's say f of x is equal to x squared when x is less than 2. F of x is, let's say, equal to 6 when x is equal to 2. Let's say f of x is equal to 4x plus 1 when x is greater than 2. All right, now you know how to draw the graph of f of x. This is a piecewise function. Therefore, you have to pay attention on which part has y equals x squared component. And of course, 2, 6 is a point. And for which part you need to draw y equals 4x plus 1. You may also use Desmos with these constraints in order to obtain the graph of this function. I'm not going to use any technology for this example. Instead, I will just draw it manually. It cannot be a difficult question for a person in a Calculus 1 class. All right, first of all, I need the axis, x and y axis. So let me assume this is my x-axis, and I also need the y-axis. Let's say this is our y-axis. All right, and then we also need to label those axes, label y-axis, label x-axis, and also we should show the origin, O. All right, now we can start drawing this graph. First, I need to, well, technically we can start from anywhere, but I'm going to first pay attention on this part, y equals x squared. It's a graph that we all know. It's a simple parabola. We know a parabolic function is something through the origin, and it's like this. Okay, and the graph exists only for this interval x less than 2. So I need to figure out the place where I have 2. Let's say 2 is somewhere here. And it's defined only for the interval where x is less than 2. That means to the left-hand side of 2. That means the branch that's going outside of x equals 2 to the right has to be erased, which I did. And also please pay attention that this constraint doesn't have x equal to. Therefore, this ending point of the graph right here should be an open dot, open circle. Okay, that's the first part of that piecewise function. We may label that graph as well. It's y equals x squared. You may write it as f of x equals x squared, or you may write it as y equals x squared. All right, so we are done with this first part of the piecewise function. Then we can look at this point. When x is equal to 2, f of x is equal to 6. That we can show on this graph. When x is equal to 2, I need the value of f of x. But before that, I can actually do something else. How about the y value right here? We know this portion that's already drawn on x and y axis, the equation of that part is y equals x squared. I know this exact point when x is equal to 2 is not defined on that piece of the piecewise function. However, when x is very close to 2 from the left-hand side, I should be able to find a corresponding y value, which is right here. So what is that y value? Well, when x is very close to 2, but when it is slightly smaller than 2, that y value should be given by y equals x squared equation. Since x is very close to 2, even though it is a little bit smaller than 2 for that left hand side, maybe it is 1.9999 or something even closer, such as 1.109 and so on. So what could be that value? That value should be approximately equal to 4, which is the same value as replacing 2 of this function x squared. 2 squared is equal to 4. All right, now we can look at this second part of that piecewise function. When x is equal to 2, the y value is equal to 6. Let's show that also on the graph. So x equals 2 is right here. When x is equal to 2, the y value should be equal to 6. So 6 could be somewhere here. Let me show it as a closed dot. I need to show the corresponding x and y values. So it is x equals 2 on that same dotted line, and that y value right here should be equal to 6. Of course, this is not drawn to a scale. Okay, now we are done with the first two pieces of the piecewise function. We are left with the last one. So the last one is y equals 4x plus 1. That graph exists for the interval x greater than 2. How do you draw that? We know y equals 4x plus 1 is a straight line, and it has a positive slope which is equal to 4, and the y-intercept is equal to 1. Any straight line with a positive slope makes an acute angle with the positive direction of the x-axis, and it has y-intercept of 1, so it will be basically a straight line like this. Please note that this inequality right here also doesn't have x equals 2. Therefore, when x is equal to 2, the end point, in fact, this starting point of that portion of the piecewise function should be an open circle. That is the value when x is equal to 2. However, I can find the value right here. How do I find that corresponding y value? We know this function, this piece of that piecewise function is defined for all the values that are greater than 2. All the x values that are greater than 2. That means if I have a value such as 2.00001, the corresponding y value should be found using this equation, y equals 4x plus 1. Since any such very close value to 2, still greater than 2, can be approximately considered to be equal to 2, therefore I will just substitute 2 in this equation, 4x plus 1. When I do that, it's 4 times 2, which is 8, plus 1 is equal to 9. Therefore, this value right here should be equal to 9. All right. Now, looking at this graph, we have 3 important points. One point is this value 4 on the y-axis. The other point is the value 6 on the y-axis right here. And the other point is this value 9 on the y-axis. For all 3 of those values, I have x value being equal to 2. So, how do we identify those 3 points? Because for all 3 points, we can see that x value is either exactly equal to 2 or very close to 2. But when I say exactly equal to 2, there is just one point that stands out, which is this point right here. When x is not exactly equal but very close to 2, we have 2 possible candidates. One is right here, the other one is right here. But those 2 can also be separated based on the fact that one is, even though very close to 2, that x value is slightly larger than 2. The other x value is also very close to 2, but slightly smaller than 2. Okay, now we need some mathematical language to write down those 3 cases. I will first look at the simplest case right here. The coordinate point 2, 6 is defined on the graph. So I can write it down this way. when x is equal to 2, the value of the function is equal to 6. Well, using some mathematical notations, we can simply write it as f of 2 being equal to 6. Very simple. And you already know that from your college algebra knowledge. There's nothing new here. That means there's technically nothing new with this point on this piecewise function. Now we are going to look at the other two cases. Now let's say I need to write down mathematically this point 2, 4. However, we know that 2, 4 is not a point on that function f of x, because if your x is equal to 2, your y should be equal to 6. But here it is not the case. We know that this highlighted point 2, 4 can be seen this way. When x is not equal to 2, but x is very close to 2, and x is less than 2. X is very close to 2 and also x is less than 2. When that happens, the value of the function is equal to 4. That is this point. So I can write that then the value of the function f of x is equal to 4. But how do we write that statement using some mathematical symbols? We can write it this way. We don't say that x is equal to 2. We can say that limit x approaches to 2. This means x is not equal to 2, but x is very close to 2. I need the value of f of x. But unfortunately, there are two possible candidates for that. When x is not equal to 2 but very close to 2, there are two possible candidates. One is right here, the other one is right here. So we have to separate those two cases. Now for this one, I'm looking at the point 2, 4. That will be the value of f if your x is very close to 2 but x is less than 2. In order to indicate that, we use a small negative symbol as a superscript with the 2 right here. In fact, this part is called the left-hand limit of f of x at 2. Now that value should be equal to 4. That's how the left limit of that function is evaluated when x is equal to 2. So this is called the left limit of f of x when x is approximately equal to 2. Simply, you can say it is the left limit. Therefore, I will go ahead and erase this part. Now, similarly, I need to pay attention on this point right here, 2, 9. We can create a similar story again, and this time we need to say when x is not equal to 2, but x is very close to 2, and x is greater than 2. In that case, then the value of f is equal to this function. When x is slightly more than 2, the value of f should be equal to the point that represents right here, which is 9. Okay, so we will write it as that. That should be equal to 9. Now using similar notations, like the notations that we used right here, we can write it as limit x approaches to 2 f of x. Once again, please note that x is not equal to 2 when you say limit x approaches to 2, but also we have to pay attention whether the x approaches to 2 from the left hand side or from the right hand side. We have this information, x is greater than 2. Therefore, even though x is very close to 2, this x approaches to a value that is slightly more than 2. Therefore, in order to indicate that, we write a plus sign as a superscript. Then this f value will be equal to 9. Now that statement is called the right hand limit. Simply the right limit. All right, so that's how the limits are evaluated. Now please note that what is this value? That is the value of the function when x is equal to 2. That was equal to 6. That is not a limit. We have two limits calculated for this function. One is the calculated left hand limit right here, which was equal to 4. The other one is the calculated right hand limit right here, which is equal to 9. So this function has two limits. Not only this function, technically any function will always have two limits. Sometimes those two limits are equal to one another, and sometimes those two limits are not equal to one another. All right, now we are done with that example. We will also look at another example. Let's say I'm going to define a new function g of x this way. My g of x is equal to, say, x squared minus 9 over x minus 3. Well, we can define it as that only if your x is not equal to 3. And let's say this is equal to 4 if your x is equal to 3. All right, now can you draw the graph of that function? Well, that is not a big deal. Just note that this part of that function can be simplified a little bit more, because when x is not equal to 3, we have x minus 3 as a common factor on both numerator and denominator, which can be cancelled. Therefore, this part of that function can be simplified to become just x plus 3, because x minus 3 can be cancelled from both top and bottom when x is not equal to 3. If x is equal to 3, that process cannot be done because it is equivalent to dividing 0 by 0, which is undefined in mathematics. All right, now what I'm going to do is I'm going to just draw the graph. First of all, I will draw the x and y axis. So here's my y axis, and I will also need the x axis. Okay, we will label the axis, x-axis, y-axis, and here's the origin. Basically, I need to draw y equals x plus 3 for everywhere except the place x equals 3. So how do you draw that one? X plus 3 is a graph like this. It has a positive slope is equal to 1, and it has plus 3 as the y-intercept. So it will be a graph like this. And the point right here is equal to 3. But it is not defined when x is equal to 3. Therefore, x equals 3, that point should be dropped from that straight line. All right, let's say 3 on the x-axis is somewhere here, and the corresponding y value should be dropped from the graph. So I will go ahead and erase this point and show an open circle. Okay, now I need to show this other point. When x is equal to 3, the y value is equal to 4. But before that, I would like to see the approximate y value right here. What should be that y value? Well, when x is equal to 3, I cannot use this equation, but I need to know the approximate height right here, which can be found simply by plugging in some value such as maybe 3.000001 or 2.9999999 for this equation, x plus 3. Since those two values are actually very close to 3, I will simply go ahead and replace 3 in this equation, x plus 3. So it will be 3 plus 3, 6. Approximately this height will be equal to 6. All right. We are done with that part. Now we look at the second portion. When x is equal to 3, the y value is equal to 4. Now we can show that value. X equals 3 is somewhere here, y value being equal to 4. That point should be somewhere here. Okay, so let's show that value on the y-axis as well. That's equal to 4. Now, using this graph, can you write down those three important values? So the first one is, when x is equal to 3, what's the value of the function gx, which is g of 3. G of 3 should be equal to the value right here, 4. In fact, it's defined in that function itself. That's also a piecewise function. It's defined as 4. So g of 3 is equal to 4. The second one, we can find the left limit. So how do you find the left limit? We can write this as limit x approaches to 3 from the left hand side. That's why I have that little negative symbol, gx. What is that value? That value is also 6. When x is slightly less than 3, such as 2.99999, I need to still go up to this point right here in order to find the corresponding y value, and that y value is equal to 6. Therefore, the left-hand limit of gx when x approaches to 3 from the left-hand side, of course, is equal to 6. Similarly, the third one is the right-hand limit. Right limit. That can be written as limit x goes to 3 from right-hand side. Show that plus sign clearly, g of x. That means if your x value is very close to 3 but little bit more than 3, in that case also the corresponding y value should be equal to 6. Alright, now there is something interesting for this specific example. We have limit x goes to 3 from left hand side g of x. That's equal to 6, and also the right hand limit is equal to 6. Therefore, we can simply write it as that. Limit x approaches to 3 from left hand side gx is equal to limit x approaches to 3 from right hand side g of x. They both are equal to 6. Well, mathematicians are efficient people. Whenever these kinds of things happen, we don't waste time writing it as left hand limit and right hand limit. We can simply write it this way. Limit x approaches to 3 g of x. This is equal to 6. This simply indicates that both left hand and right hand limits within a neighborhood of 3 will be equal to the same value, and that value is equal to 6. All right, so whenever you have the same left hand limit and the right hand limit, you don't need to specify plus or a minus sign as a superscript with the 3. One more quick point. Whenever your left hand limit is equal to the right hand limit, we say that the limit exists. We say limit exists. More completely, limit exists within a neighborhood of x equals 3. However, I have one more question. Is this function continuous with respect to x equals 3? Or in other words, is this function continuous within a neighborhood of 3? Unfortunately, it is not continuous. We can of course see that there is this discontinuity right here. We can also visualize that graphically, even if I don't have the graph. If I have these calculated numbers, we can see it. Even though the limit exists, the limit is not equal to the value of the function when x is equal to 3. The value of the function when x is equal to 3 is equal to 4. That is not equal to 6. Therefore, the function is not continuous. So we can write down that statement as well. G of x is not continuous within a neighborhood of 3. So we can write the reason because of this symbol, 3 dots written like that, is called because of, or in other words, the reason is. So the reason is that the limit x approaches to 3, g of x is not equal to the value of the function g evaluated at 3. Now, here's a quick comment. What if your left hand limit and right hand limit are not equal to one another? Or in other words, if the limit does not exist, can the function be continuous? Of course, the function cannot be continuous. Because if your left hand limit, let's say in general, approaching to a from left hand side, some function f of x, if this is not equal to limit x approaches to a from the right hand side f of x, we say that the function is not continuous at x equals a. Even if these two limits are equal to one another, or in other words, even if the limit exists, if the value of the function is not equal to the limit, the function is still not continuous. So we will write down that as well as another comment. If limit x approaches to a, f of x exists. What does that mean? That means left hand limit evaluated at a for fx is equal to the right hand limit evaluated at a for fx. If they are equal to each other, then the limit exists. Even if the limit exists, but if limit x approaches to a, f of x is not equal to the value of the function evaluated at a, then f of x is not continuous at x equals a. Okay. All right, we can now look at another third example if you are interested. Here's my third example. We will simply look at another function, let's say h of x. It is just say x squared. So it's not a piecewise function, it's a complete function given. And if you would like to draw that function as well, we can quite easily draw it. It's a nice parabola, very well known parabola. So these are my axes. We need to show the origin, label the x-axis, label the y-axis. All right, let me go ahead and draw that function, the graph of the function. It will be like that. Let's say I'm interested in a point like this. Let's say that value is equal to 5. We know for all the values of x, this function is very well defined. Therefore, if I would like to find the value of this function right here, that value is actually equal to what? What is this y value? If I substitute 5 for x, I get 5 squared as the y value, so it's equal to 25. Now for this function, we can write down those three pieces. First piece is, what's the value of hx evaluated at 5, or in other words, h5. h5 is equal to 25. That is the first part. The second part, limit x approaches to 5 from the left hand side h of x. What should be that value? X approaches to 5 from the left hand side means x is very close to 5, but it is not equal to 5, and it is less than 5. That means a value such as 4.99999. And very clearly, using this graph, we can say that value should also be approximately equal to 25. Therefore, we write it as that. The left hand limit is equal to 25. Similarly, the third step is to find the right hand limit. Limit x approaches to 5 from the right hand side. Don't forget that little plus symbol as the superscript, h of x. So what is that value? Now x is slightly more than 5, but very close to 5. Even that value should be equal to 25. All right. Therefore, this is equal to 25. All right, very good. We have the left hand limit being equal to the right hand limit. So we can provide one limit looking at those two cases. That is, we can simply write down limit x approaches to 5 h of x, that is equal to 25. Very good. Now, is this function continuous within a neighborhood of 5? Or in other words, is this function continuous at x equals 5? Of course, yes. That is because we can see that the limit exists, which is the first condition. Left hand limit is equal to the right hand limit, and that's equal to 25. And that value is also equal to the function evaluated at x equals 5. They are all equal to 25. Therefore, we can conclude this way. We write limit x approaches to 5 h of x is equal to h of 5. Of course, they both are equal to 25. Now, because of that reason, we say h of x is continuous at x equals 5. Please also note that if necessary, this part can be replaced by both left and right hand limits. You may write limit x approaches to 5 from left hand side h of x is equal to limit x approaches to 5 from right hand side h of x is equal to the rest h of 5, and everything is equal to 25, and therefore we conclude that h of x is continuous at x equals 5. All right, this is the complete discussion on evaluating limits graphically. Later we will see how to evaluate the limits numerically. All right, thank you so much.